Dear viewer, here is one indicating instrument. Let us consider a magnetic field created by the two poles of a permanent magnet. A set of conductors are placed perpendicularly in the magnetic field. They carry current in opposite directions. The conductors are joined together forming a coil of n turns. Now, the Fleming's left-hand rule is applied in the arrangement. For a left hand, forefinger points to the direction of magnetic field. The middle finger indicates the current direction. Consequently, the thumb points to the direction of generated force. This force, F, is equal to the product of N, the number of turns of the coil, B, the flux density, I, the current in one side of the coil, and L, the length of the coil perpendicular to the field. If D is the separation between two coil sides, that is, the separation between two forces, then a torque sets in, which is the product of the force F times the separation D. This torque causes the coil to deflect. A spindle runs through the former and acts as the axis of deflection of coil former assembly. The top view of the whole structure becomes schematically, the entire structure looks like this. The deflecting torque Td equals to the meter constant G into the coil current I. Ideally, the deflecting torque does not depend on the deflecting angle theta. After a certain deflection, however, the deflecting torque Td should be counterbalanced by an opposite torque. This torque, Tc, called control torque, is produced by a pair of springs attached to the spindle on both sides of the former. As the deflecting angle theta increases, control torque Tc increases. When the coil former assembly deflects, springs get twisted and deformed. As a result, it exerts an opposite torque Tc. On comparison of the two torques Tc and Td, a certain angle of deflection θf is obtained when two opposite torques Td and Tc become equal. The moving system containing the pointer attains a steady deflecting angle θf. As a result, the particular steady-state angle to which the pointer sticks is proportional to the applied current I in coil. Each of the two springs has two different roles to play. First, it offers control torque. One end of the spring is attached to the moving spindle. The other end is attached to the fixed base of the instrument. As the spring deflects, the moving end of the spring gets twisted. The spring deforms and the opposing control torque sets in. The second role of the spring is a bit tricky. The fixed end of the spring allows incoming current. This current comes from external circuit under measurement. The moving end of the spring guides this current along the spindle towards the moving coil of the former. The spring material therefore should be electrically conducting. Here is the demonstration of a practical instrument showing essential features of construction. The coil former assembly immersed in the magnetic field of a permanent magnet is free to deflect up to a certain angle.